Hello students, welcome to the third video on advanced power electronics in which we are studying resonant converters. So today we are going back and we are going to study basic resonant circuit concepts. First we will see series resonant circuits, then we will move to parallel resonant circuits. In series resonant circuits, the first circuit that we will see is the undamped series resonant circuit, which you can see on the screen. Herein we have a DC voltage source Vd and a resonant circuit consisting of LR and CR connected in series. The inductor current is IL and the initial value of the inductor current is IL0. The capacitor voltage is Vc, wherein the initial capacitor voltage is Vc0. Now if we take the inductor current and the capacitor voltage as the state variables, okay, I'll digress here. I've already sent you the PDF. I'll go there. So this is the undamped series resonant circuit that we just saw. So if we take the inductor current IL and the capacitor voltage Vc as the state variables, then the state equations for this circuit are LR dIL by dt plus Vc is equal to Vd and CR dVc by dt is equal to IL. Now I think we have studied state variables in control systems before. We need to solve these state equations. Number of methods are available. I think you also must know at least 3 methods. First is solution of simultaneous equations, linear differential equations that you must have studied in maths. The second method is by solution of the state equation. Now these state equations can be in the form x dot is equal to ax plus bu, and the solution of this state equation is x of t is equal to e to the power 8 into x of 0 plus e to the power 80 integral 0 to t e to the power minus a tau b u of tau d tau. So I don't know whether you have studied this or not. So actually for these are very simple equations, so we don't need to go by that method here. I'm going to solve them here simply by using the Laplace transform. So I'm taking t0 is equal to 0 and solving them for simplicity. So if we take the Laplace transform of equations 1 and 2, and the Laplace transform of equation 1 will be LR, Laplace transform of dIL by dt is SIL of S minus IL0, where IL0 is the initial inductor current, plus Vc of S, that is equal to the Laplace transform of Vd is Vd by S. And similarly, the Laplace transform of equation 2 will be CR into S Vc of S minus Vc0, where Vc0 is the initial capacitor voltage, that is equal to IL of S. So if we rearrange equation 4, we see that Vc of S is equal to 1 upon SCR IL of S plus Vc0 by S. And if we substitute this in equation 3, this is the equation that we get. If we rearrange it, keeping the variable IL of S on the left hand side and the other parameters to the right hand side, this is the equation that we get. It can be simplified. And the left hand side then becomes LR CR S squared plus 1 upon SCR into IL of S, and the right hand side is LR IL0 plus Vd minus Vc0 by S. So if you keep only IL of S on the left hand side and all the remaining terms on the right hand side, then this is the equation that you get. This is the equation that you get. If you divide both numerator and denominator of both these terms by LRCR, the equation that you get is S upon S squared plus 1 upon LRCR IL0 plus 1 by LR Vd minus Vc0 upon S squared plus 1 upon LRCR. So we can let 1 upon LRCR be equal to omega 0 squared, or omega 0 is equal to 1 upon under root of LRCR. That is called the angular resonant frequency. And then IL of S becomes equal to S upon S squared plus omega 0 squared IL0 plus 1 upon LR Vd minus Vc0 upon S squared plus omega 0 squared. Now if we take the Laplace inverse, IL of t becomes equal to IL0. The Laplace inverse of S upon S squared plus omega 0 squared will be cos omega 0 t plus Vd minus Vc0 upon LR, and the Laplace inverse of 1 upon S squared plus omega 0 squared will be 1 upon omega 0 sine omega 0 t. Now, this omega 0 LR term, if we substitute the value of omega 0, this becomes under root of LR by CR, that we can call Z0, that is the characteristic impedance in form. And so then IL of t becomes equal to IL0 cos omega 0 t plus Vd minus Vc0 upon Z0 into sine omega 0 t. The capacitor voltage, this is the inductor current. The capacitor voltage can then be found by using the standard equation 1 upon CR integral of IL of t dt. If you integrate IL of t, this is the equation that you get, IL0 by CR sine omega 0 t by omega 0 minus Vd minus Vc0 by Z0 CR, Z0 CR cos omega 0 t upon omega 0 plus a constant of integration, that is C1. Now 1 upon omega 0 CR, if we calculate this, this comes out to be under root of LR by CR, that is equal to Z0. So this term 1 upon omega 0 CR becomes equal to Z0, and Z0 CR omega 0, if you calculate it, it turns out to be equal to 1. If you substitute this, Bc of t becomes equal to Z0 IL0 sine omega 0 t minus Vd minus Vc0 cos omega 0 t plus C1. Now the constant of integration C1 can be found by using the initial condition, that is at t is equal to 0, the capacitor voltage is Vc0. If you substitute this, you get the value of C1 as equal to Vd. And if you substitute this back in equation 6, the capacitor voltage becomes equal to Vd minus Vd minus Vc0 cos omega 0 t plus Z0 IL0 sine omega 0 t. So these are the solution of the equations A and D, are the solution of equations 1 and 2. Here I am again displaying the solution, but this is from Ned Mohan's book. I had taken T0 is equal to 0. He has not taken T0. He has not taken T0 equal to 0. He has taken T0 as it is. So if you plot this inductor current and the capacitor voltage in per unit, where we can take the base voltage as Vd and the base current equal to Vd by Z0. So if you plot it in per unit, these are the waveforms that you get for initial inductor current equal to 0.5 per unit and initial capacitor voltage equal to 0.75 per unit. So what you see basically is that the inductor current is a sinusoid that is passing through 0 at regular intervals. Those intervals are decided by the angular resonant frequency omega 0. The capacitor voltage is also a sinusoid, but it has been shifted upward by a value of Vd. Whatever may be the value of Vd, it has been shifted up by that value. The next circuit that we can see is a series resonant circuit with a capacitor parallel load. Here the input is a DC voltage Vd. Again, we have a series resonant circuit consisting of LR and CR. The inductor current is IL, whose initial value is IL0. The capacitor voltage is Vc, whose initial value is Vc0. The difference is that there is a load represented by the constant current I0 connected in parallel with the capacitor. Again, if we write the state equations here, taking the inductor current IL and capacitor voltage, which are the state variables, then this Vc is equal to Vd minus LR dIL by dt, and the inductor current IL minus IC is equal to I0, or IL is equal to I0 plus IC. If we solve these equations as we did earlier, this is the solution. Now, as you can see, both IL and Vc have been shifted upwards by value I0 and Vd respectively. If you consider the special case where the initial capacitor voltage is 0 and the initial inductor current is equal to the load current I0, then these equations reduce to IL of t is equal to I0 plus Vd by Z0 sine omega 0 t minus t0, and Vc of t is equal to Vd 1 minus cos omega 0 t minus t0. If you plot these two waveforms, again on per unit basis with Vc0 is equal to 0 and IL0 is equal to I0, that is equal to 0.5. These are the waveforms that you get. As you can see, both the inductor current and the capacitor voltage are passing through 0. However, the 0 crossing instants are different. The frequencies are same, both have the same frequency decided by the components LR and CR. And frequency is basically omega 0. The next type of resonant circuits are the parallel resonant circuits, in which we will consider only one case, that is the undamped parallel resonant circuit. This is an undamped parallel resonant circuit where the input current is now constant at ID, and we have a parallel resonant circuit consisting of LR and CR. The inductor current is IL, initial value is IL0, capacitor voltage is VC, initial value is VC0. So again, we can write the state equations. This ID is equal to IL plus the capacitor current, that is CR dVc by dt, and the capacitor voltage is same as voltage across the inductor, that is LR DIL by dt. If you solve these two equations, again you are getting these sort of equations where once again omega 0 is the angular resonant frequency given by 1 upon under root of LRCR, and Z0 is the characteristic impedance in ohms given by under root of LRCR. As you can see in this case, the capacitor voltage does not have any offset. It will be a pure sinusoid passing through 0 at regular intervals. The inductor current does have an offset of ID. Okay? So it can or it cannot pass through 0 depending on what is the value of ID. So that is the end of this video. What we learn from here, or what we learned today, is that if we introduce a resonant circuit consisting of LR and CR after the DC voltage, after the supply voltage or current, and before the load impedance, it is possible to have the input current as well as input voltage, either the input current or the input voltage or both of them, to pass through 0 at regular intervals decided by the components LR and CR. Because the current and voltage are passing through 0, it is possible to have 0 voltage switching and 0 current switching. How it happens, that we will see in the next lecture.